Hello, welcome to Maths with EJD. Well, for now, I think this will be the last video on power series. Of course, if something else comes up afterwards, I may have to attend to it. But by my estimation, this should be the last video in this series. So, and that is it's ending on this nice note of knowing the applications of power series. Probably I've mentioned a bit of that in the process of making the videos. But here we focus really on that. That of course, power series have various application, various practical, applications across mathematics and science, across mathematics and science. Okay, so let's start with the first one. Solving differential equations. So power series can be very useful in solving differential equations. I am here to make a playlist on differential equations, but I should get to that at some point. Okay, solving differential equations. Okay, so power series are instrumental. They are instrumental in finding solutions to differential equations, especially when exact solutions are challenging to obtain, are challenging to obtain. Okay, I know in the course of taking courses on differential equations, I remember very well when we talk about things like Bessel functions, Frobenius, and all of those kind of things. We get to use power series solutions to solve them, and it can be quite tricky. So, but I mean, power series offers some kind of solution if you cannot get exact solutions. So this approach involves expressing the solution, as a power series, and then substituting it into the differential equation. That's the procedure. Substituting it into the differential equation to determine the coefficients. Okay. So a very good example would be consider the differential equation. Consider the differential equation y prime prime. This is the second order differential equation. Y prime prime plus y equals 0. Okay, so we can solve this by assuming a solution of the form y of x. So of course the solution to this differential equation will be two values of y1 and y2. So and then we can take this series form as a possible solution to it. So we can take a solution of the form summation from n equals 0 to infinity of an xn. So we take this as a solution, and it means we need to differentiate twice, so you differentiate time by time twice, and then you go on. So you need to get like y prime of x, which is summation from n equals 0 to infinity, and that is an x raised to power n minus 1. And then you go again. I'm not solving this problem, actually. I'm just explaining. So, I mean, do we have a shift now? Like we shift one step. or so. And then here we shift second step to infinity, and we have an, then n into n minus 1, x raised by n minus 2. So you have this, and then you substitute all of this into the original equation, and then you try to solve and, get all of that. So that's what I've done there. So by differentiating term by term, which we saw in the previous video, by differentiating under differentiation now, by differentiating term by term and substituting into the differential equation, into the differential equation, we find a recurrence relation. Find a recurrence relation for the coefficients. So we're basically looking for the coefficients. For the coefficients an. So solving this recurrence relation gives us the series solution. Okay, so that's one application. So you can solve differential equations using power series. So next we can talk about approximation of functions. So you can approximate functions using power series. That's what this is about. So power series are often used to approximate functions that are difficult to handle analytically. Okay, because we can truncate, right? So by truncating the series, to a finite number of terms, we saw that previously, to a finite number of terms, we can obtain polynomial approximations. So power series can help you so using power series, right, you can change transcendental functions that are naturally not polynomials, like hyperbolic, trigonometric, logarithmic functions. So you can, transform them into power series with and truncate the terms. So by doing that, we can obtain polynomial approximation of the function. Okay. And we have an example to drive the point home. So say that you have the exponential function, e raised to power x can be approximated. We've done that a couple of times. Can be approximated by four terms of the Maclaurin series, such that e raised by x is approximately 1 plus x squared over 2 factorial plus x cubed over 3 factorial. So we've done this in fact, we did this a lot in the video under power series representations of functions. So we estimated things like this. So this approximation becomes more accurate, and we saw that practically. I demonstrated using Desmos. This approximation becomes more accurate as more terms are included, So you keep where you truncate will be dependent on, will be determined by how much accuracy you are looking for. So that's important. So if you want more accuracy, you take more terms. So that's the second application. Then we can talk about numerical methods. Numerical methods. Because numerical methods are generally used also whenever you cannot get analytical solutions to your problems. So numerical methods. So in numerical analysis, power series can be used to develop algorithms for solving problems where exact solutions are impractical and not practically obtainable, right? They're impractical. For example, series expansions are used in iterative methods for solving nonlinear equations and in numerical integration. Numerical integration is where you use things like trapezoidal rule, Simpson's rule, and all that. Okay, consider this example. Newton's method, right? Newton's method for one day soon, I think I should also talk about numerical methods. Newton's method for finding roots of functions can be enhanced using series expansions to estimate function values and derivatives more accurately. Okay, so that's for numerical methods, we can use power series too. Then we go for the fourth application. Really very important applications. Look at physics and engineering. So power series can come in handy in physics and engineering. Okay, so power series are frequently used in physics and engineering to model systems and solve problems involving small perturbations. So I've worked on projects a couple of times where I've had to use things like this, asymptotic expansion or something like that. So and solve problems involving small perturbations. Okay, series expansions are used. They are used to approximate solutions to problems, solutions to problems in mechanics, electromagnetism, and other fields, So let's see an example. In mechanics, the motion of a pendulum, the motion is a common thing. The motion of a pendulum for small angles, okay, for small angles can be approximated, using the power series expansion of the sine function, which we have come across a couple of times. So which is sine theta is approximately theta minus theta cubed over 6 plus theta raised to 5 over 120, because being an odd function. So, theta minus theta cubed over 3 factorial plus theta raised to 5 over 5 factorial. 5 factorial is, of course, 120. So this approximation simplifies the analysis of pendulum motion. Okay, so we come to the fifth example, which is a field I've collaborated with a colleague in this area a lot, talking about analytic functions and things like that. So the fifth one is complex analysis. So power series are useful in complex analysis too. So in complex analysis, power series are used to represent analytic functions. And to study their properties. Okay, so if you want to study analytic functions, you can use power series. I mean, this is seriously used in this field. Fields like univalent functions and all of those kind of functions. So the Laurent series, a generalization of the Taylor series, is used to handle functions with singularities, meaning functions that are not defined as particular points, like maybe something of like 1 over x minus 1, for instance. It won't be defined as x equals 1. So Lorentz function can take care of that. So it's used to handle functions with singularities. So example, the function 1 over 1 minus z can be expanded in a power series in a power series around z equals 0, because you know that function is not defined as 1. When z is 1, you have 0 under there, and that will be undefined. So because of that, it can be expanded in a power series around z equals 0, you know, such that you have 1 over 1 minus z. It looks a lot like the geometric function, the geometric series. We have summation from n equals 0 to infinity for z raised to power n. So this series is really important in complex analysis. So this series representation, this series representation is useful for analyzing the behavior of the function in complex domains. Okay. So with that, we come to the end of what I can say, maybe the whole of power series, possibly, except something comes up later. All right. So if you have followed up to this point, thank you so much for coming. Keep coming, because there are so many other things going on in this channel. So if you have not subscribed, be sure to do that. And of course, hit the notification bell so you can always get alerted when a new video is released. Then don't forget to comment, like, and share. For instance, this the videos I've made on power series, on vectors, and on hyperbolic functions, they actually comments from a friend who would like me to make videos on them. So if you have such needs, you can just let me know, and I might just have time to do them. Thanks for always coming by. See you next time. Bye.